sometimes we want to take the complement of an entire function, and we'll see later why we'll want to do that. That's if we want to implement with inverse logic, like with NANDs and NORs gates instead of AND and OR gates. And we'll use De Morgan's theorem to complement a function. So when we complement a function, essentially what we want to do is we want to replace all the functions when it's equal, the function's value, when it's equal to 0, we replace it with a 1. When it's equal to a 1, we replace it with a 0. So here we see, for example, if our function is just x or y, the complement of that, x or y naught, is just a 1 whenever the OR function is a 0, and it's a 0 when the OR function is equal to a 1. And we can show then by De Morgan's theorem that that's equal to x prime, y prime. And that is De Morgan's theorem. We can verify that within our truth tables. That's where the De Morgan's theorem will come in very handy. So what if we want to use more than just two variables though? De Morgan's theorem is just defined with two variables, and we often have to work with functions that are of 3 or more variables. So let's look at the example here for 3 variables. If we have a function of a, b, c, so a or b or c, if we want to invert that, well, we need to convert that to 2 variables to use De Morgan's theorem. So we'll just let our x equal b or c, and we'll continue. So then we have that a or b or c prime is equal to a prime x prime by using De Morgan's theorem. And then we can expand it again. We can expand back x is equal to b or c, and then we see we have De Morgan's theorem again that we have to evaluate on our b or c. So we have a prime, and then in parentheses, b prime, c prime. So then we can use our associative theorem, and that's just a prime, b prime, c prime. So it does work for 3 variables. In general, it works for any number of variables. No matter how many variables we are ORing within the parentheses and then negating them with our inverse, then we can change that to just the inverse of the AND, or the AND of the inverse of each variable. So basically we interchange our AND and OR, and we complement each literal. So if we want to find the complement of this function here, we can do that with both of the 2 methods. We could use De Morgan's theorem twice. So we have our f, and typically I'll be using f prime, but I also want to show that f with a bar over it, that's also means the complement of the function f, and this is f1. So we substitute in for f1 our algebraic expression, and we put that in parentheses and then complement the entire function. So then we apply our De Morgan's theorem. We convert this OR to an AND, and then we complement these 2 terms, right? So this term x prime y z prime becomes, we can consider that, a capital A and that a capital B. We've just eliminated that substitution step. But we make sure we put these in parentheses so we use our order of operation properly, and we're complementing this entire term now. So when we complement this term, we can use De Morgan's theorem again and convert all these ANDs to ORs and complement each of these literals. So the complement of x prime is x prime prime. Well, then we have to use our involution theorem. That's just equal to x. The complement of y is y prime. The complement of z prime is z prime prime. And we can show that with involution theorem, that's equal to z. And similarly, on this other term, we're still ANDing. We're just using De Morgan's theorem on each of these 2 AND terms, converting them to OR terms, and complementing each literal. And we end up with x or y prime or z, that entire OR term, ANDed with this OR term x or y or z prime. Our other option is we can take the dual of the function and complement each literal. So the dual then of f1 is where we just replace the ANDs with ORs and the ORs with ANDs. So this AND term becomes this OR term. This OR becomes an AND. We just show that by 2 parentheses next to each other. And of course this AND term becomes this OR term. And then we complement each literal internally, and we end up with the same result. So if we want to try that on this function here, f3, why don't you pause the video and give that a try. All right, by using De Morgan's theorem, we will just show here our f3 prime, and we'll put our entire expression in parentheses, we'll prime the whole thing. By order of operation, we evaluate this prime or this inverter first, and that becomes equal to our x. Well, we'll do this in blue. Our x prime, but we've got to prime it or complement it. And then this and becomes an or. And then the other term here is in parentheses, that's our x, excuse me, that's a y z prime or y prime z, and we invert that entire thing. So now we've evaluated this complement, but now we need to still evaluate this complement and this complement. So this is just then equal to, by involution theorem, x prime prime is equal to x. And then we're going to OR that with, when we evaluate this, this complement here, we'll show it in green, this complement here, we'll do our y z prime, but we have to prime that term. We change this OR to an AND. We'll just show them next to each other. Y prime z. We complement again, and then we can use De Morgan's theorem one more time. We get x or y prime or z prime prime, and we haven't affected this AND. We've just affected this AND. This AND became an OR down here, and then we have our y prime prime ORed with z. And then we can rewrite that as x or y prime or z. We can, or y. This should have been a prime here, right? We didn't pull this prime in, so y or z prime. So we just further express this. So that's by using our De Morgan's theorem multiple times. If we do just take the dual, right? We take the dual and complement each literal. Let's try that. So the dual would we would have x prime. The dual of this and would be an or, and then we'd have, we're not complementing each literal yet, and then we'd have or y or z prime anded with y prime or z, and then so that's just taking the dual, and then we'll complement each literal. We get a prime, a prime, a prime, a prime, a prime, and evaluating our involution theorem, that's our x or y prime or z, y or z prime. All right. What we'll see later is, we won't evaluate that here, but we could further try to simplify this. These wouldn't be very well simplified. Oops. In fact, y z prime or y prime z, that's equal to y exclusive or z. And what we have down here is that this is equal to x ORed with y exclusive or z prime. And you'll see that later. So lastly, let's just look at what happens when we complement the complement of a function. So we know what F4 is. It's a little bit different than it was in the last one, almost the same. But F4 prime prime, the double complement. By involution theorem, we should expect that that's just equal to F4, right? So if we do just the single prime on this, F4 prime, that's going to be equal to x ORed with y prime, z prime, or yz. and all of that primed. If we want to complement it again, we'll complement it again with the green here. So complementing it again, we take this whole thing, we'd have to complement again, and then that would be equal to x prime ANDed with y prime, z prime, or yz, and then we get our, that prime comes down, and this prime, and then we, if we use involution theorem on this, x, we get x prime, x prime, y prime z, or yz. Now that's not quite the same, is it? But we made a mistake here. Did we? We made a mistake right here, right? When we did the first prime here, we needed to do x prime or, so we dropped that prime. So that becomes prime prime and the prime prime by involution theorem. We get back to the same function. So we can show then that in fact, whatever the function is, f prime prime is just equal to f. So we're using involution theorem on our function. This is going to be important for us later as well when we're trying to implement circuitry.